So in this problem, we're asked to figure out what the velocity of a person might be if they went skydiving and fell through the air for a minute or two before opening their parachute. So in this problem, we're going to assume a drag coefficient of 0.5 and an air density of 1.2 kilograms per meters cubed. So first, let's start off by drawing an isolation diagram of the person. So here we have our person, and we're going to take the y direction to be positive in the upwards direction. So we have the force of gravity, mg, acting on the person in the negative y direction. We also have the drag force, which we will call F of d, acting in the positive y direction. So now by Newton's second law, we have that the net force, F net, is given by the drag force minus mg, and that's going to be equal to the mass of the person times its acceleration. Now, since the person has been falling through the air for 1 or 2 minutes, it would be not too inaccurate to say that the person has reached terminal velocity. So we're just going to assume that the person has reached terminal velocity, which means that their acceleration at this state is going to be 0. So this means that if we rearrange the terms, the drag force is going to be equal in magnitude to the force of gravity on the person. Now we know that the drag force is given by the coefficient, drag coefficient, multiplied by the air density rho, multiplied by L squared, where L is the typical linear dimension associated with the drag force, multiplied by v squared, where v is the speed of the person. And at terminal velocity, that's going to be equal to mg. So now, rearranging terms, if we isolate for v, we get that v is going to be equal to mg over the drag coefficient times rho times L squared, all square rooted, which is just going to be equal to L. Let's leave that out first. So now we know that G is going to be equal to approximately 10 meters per second squared. So if you plug in our values for G, drag coefficient, and rho, we're going to get that the speed is equal to the square root of m times 10 meters per second squared, all over 0.5 times 1.2 kilograms per meters cubed times L squared. And if we simplify everything, we're going to get that this is going to be equal to 4 meters per second squared over L times the square root of little m over 1 kilogram. So now we have an expression for the final speed of the person in terms of their mass and the typical linear dimension. So now we have to figure out what values to substitute for m and L. Now, for convenience sake, we're going to take m to be about 36 kilograms, which is not too off the average mass of the person. And now for the typical linear dimension, we're going to take the average width of the person, since the drag force is going to be mainly the air resistance that the person feels when they fall through the air, which is going to be proportional to the cross-sectional area of the person as they fall through the air. So it'd be reasonable to take the typical linear dimension to be the width of the person, which we will estimate to be about 0.25 meters. Now, of course, you can use different values, but here we're just going to take some approximate values to get a nice number. So if we substitute that in, we're going to get 4 meters per second squared divided by 0.25 meters times the square root of 36 kilograms divided by 1 kilogram. So that's going to leave us with a final answer of 50 meters per second. So that's going to be a pretty good estimate of the speed of a person who's falling through the air without a parachute for about 1 or 2 minutes.